We're Pipeline Design and Engineering, and we're going to show you some examples of real-world injection molded parts and dive into some of the details a little bit more here. First part we're going to look at is this guy right here, and this is actually this actual part that I have right here on the table is not injection molded. It is 3D printed, but it was designed to be injection molded.
Could I ask you, how can you tell if it's 3D printed?
Well, you can tell by the surface finish. Let's see if I can get this in the light. You can see some layer lines right here. 3D printing works by depositing one layer at a time and then moving a little bit, and you can kind of see that this particular set of parts was made via the FDM 3D printing technology, or fused deposition modeling.
And plastic injection molding will look more like this then?
Yeah, so this surface here you can see is much more smooth. There's no indication that there are layer lines or individual layers built up in that part.
Okay, so why is it that we want to use a 3D printed part for these purposes?
We prototype this. Before you start injection molding a part, you want to make sure that your design works, because the tooling for injection molding is very expensive, and you don't want to invest in that tooling until you're very confident that your design works. So instead of paying, $15,000, $20,000 for an injection molding tool, we paid about $300 or $500 for this 3D printed part.
Okay, so it is common practice to perhaps do a 3D printed version before you dive into the injection molding? Very
common. Yep, that is how it's done. It's a cheap way to fail. The reason we're going to look at this part is, even though it's not actually injection molded, it was designed to be injection molded, and it has some features that are educational. So let's take this apart. Maybe I'll give you a quick demo of what it does. It's a cable holder. So you would put a bundle of cables in here, and there's just a handle that you can carry it. And there's a little button up here, so you can take the teeth out. The ratchet action inside there. Now you can, it's stuck. Okay, so taking this apart. The first thing that you'll notice maybe is that it's hollow inside here. There's a lot of empty space. And the reason it's hollow is because for injection molding, one of the key principles, the design rules, is that you have to maintain a standard wall thickness. So you'll see that the wall thickness is the same pretty much everywhere in this part, and that's one of the telltale signs that this was designed to be injection molded. Same thing with this little release button trigger here. You can see that in this area right here, there's a pocket in there, and this pocket is a cord out feature. In an earlier video, we talked about the core side of the tool and the cavity side of the tool. Well, for this particular part, there isn't really a core side or a cavity side, because you're pulling half the tool out of this side and the other half of the tool out of this side, and the only part that's really visible to the user is this area right here. Everything else is inside. Another cool thing that you can do with injection molding is you can design a spring into your part, and it's this spring right here, this living spring on the part, that allows for that ratcheting action without any additional components.
I don't understand. What do you mean by spring?
Okay, let's put this part on here, and you can see how that arm acts as a spring to push this this catch back down.
Okay, but you can create this spring feature with also a 3D printed part, right?
That's right.
Okay. That's
right. Yeah, you can. In fact, you could create that with a machined part as well.
I want to ask you about the wall thickness. So this is wall thickness here. Would this also be wall thickness on the back?
Great question. The term wall thickness can be confusing to someone who has never heard it before. So wall thickness is what we measure, like right there. So we have a wall thickness of about 125, 126 thousandths of an inch. Over here, our wall thickness is about 76 thousandths of an inch. And that's actually a good point too. When you have ribs in a part, or anything that isn't like the fundamental foundational geometry of the part, you want those ribs, or in this case they're bosses. Oh, a rib. So like this right here, that's a rib. And you can see several of them. Here's a rib right here. And there are, some ribs over here as well. And ribs are used as structural supports. So ribs make the part stronger. In this part here, you can see we have some ribs there and there and there. But a rib is an efficient method of adding structural rigidity and strength to a part without just filling the entire part with material, which you don't want to do because then you would not have a constant wall thickness.
Should the ribs be the same thickness as the wall?
Typically, you want your ribs to be about 60 to 80% of the thickness of your nominal wall section. So in this example, our nominal wall is right here, 125-ish, and our boss is about 0.72. So I don't know what the math is in my head, but hopefully that's somewhere between 60 to 80% of the nominal wall thickness.
What's a boss?
A boss is a circular protrusion like this. Oftentimes you'll hear the term screw boss. A screw boss, we don't have any on this part, but a screw boss would be the circular protrusion into which you screw and engage a screw. They're very common in consumer products where you'll have like a clamshell design. You'll have two plastic halves that need to be joined, and you'll have a screw that goes through one half and engages a screw boss in the other half.
So you mentioned wall thickness. Is this a wall from the way it sounds like it, but is this also a wall here? Is this a wall or no?
Yes, it is. If you were to cut this part in half right here and look at it in that direction, let's draw a little picture. So let's see, we're cutting the part right here and we're looking at it in that direction. You would see something like that. It would look like an H. And we'll do our cross hatching to indicate that this is solid material we're looking at, not a cavity or a hole or empty space. And so we have several wall thicknesses here. That's a wall thickness, that's a wall thickness, that's a wall thickness. These are all wall thicknesses. And these would all be nominal wall thicknesses.
What does that mean, nominal?
Nominal is like your main wall thickness, the most common, or the fundamental wall thickness.
And should these wall thickness be all the same thickness, or no?
These ones would, yeah. For this part in particular, this is a pretty structural part. The reason that you use smaller wall thicknesses for ribs than you do for your nominal wall is because when you have a thick volume of material, you will often see what's called sink on the other side. Now this is 3D printed, and hopefully my ribs are well designed there so you can't really see it, but let's go back to this sample part. Let me zoom in a little bit. Now I mentioned in another video that this section right here was intentionally created thicker than the other walls. You can see it's almost twice as thick. And let's see if we can get the light just right. Yeah, you can see here on the sides how it's sunken in. It's sunken in there, and that is what we refer to as sink. It's a cosmetic blemish. People don't like to see it. It looks like a mistake, and that is what happens when you have thick volumes of material next to your nominal wall thickness.
So what could manufacturers of this part have done to prevent that sink from forming?
Well, what they would have done is make this wall thickness the same as the other three. So, right here, let's measure this. That is about 80 thousandths of an inch, a little bit less, maybe 70. And I'm guessing this one is, oops, This one will be about the same, 77. And this guy here, that's 135. And because it's so much thicker than the other, than what I would call the nominal wall thickness would be, these guys about 70 thousandths. And because this is so much thicker, you end up with that sink.
Okay, cool. Well, if you want to show us some other parts, maybe. Or?
Yeah. So let's move on to some other parts. This one here is an Allen key driver. So it's a hexagonal tip used for driving like button head cap screws or socket head cap screws. Screws in which the head contains a hexagonal hole for engagement to be driven in. But what's interesting about this part is it has a very clear parting line. Now usually you don't want to see the parting line because it's a cosmetic blemish, but it's an inevitability of injection molded parts just due to the nature of how injection molded parts are created. Can you grab that sample tool again? Yeah, thank you. Looking at our sample tool, right, we have the core and the cavity halves of the tool, and in the middle of them, right here, this is where a parting line would be created. Now, for this part, the designers were very clever, and they designed it so that the parting line is at the very bottom of the part, so it's hidden. You can't really even tell that there is a parting line. But the designers of this part, and this is a very low-cost, cheap part, and so the manufacturer probably didn't care very much that there was a parting line that would exist right in the middle. And this is even more evident just because this has been used and there's some dirt in it that's gotten caught in that parting line. But you can feel that there is a very definite parting line there, and that's what's created between the two halves of a tool.
What could cause a more pronounced parting line?
If the two halves of the tool are not aligned very well, for example, ideally you would want the edge of your tool, that's maybe the cavity side on top, and then this is maybe the core side on bottom. You'd want these edges to line up perfectly, and you'd want these corners, you'd want these corners to be perfectly sharp. Well, in reality, nothing is ever perfectly sharp. There's going to be, a little bit of rounding there, and that's where your parting line is going to exist. Sometimes, though, the parting line will be due to a mismatched core and cavity side of the tool. So if there's an offset like this, that would create a much bigger parting line. And the one that I feel here, this is actually a pretty big parting line. When manufacturers are being careful and trying hard to avoid the parting line, you wouldn't see near the amount that we see on this part.
Couldn't a pronounced parting line like this one also be shown because the maintenance on the tool is not the best?
Could be. Over time, tools wear down, certainly. And we talked about the rounding of corners over here. You might start off a tool where there's only a few thousandths of an inch radius on those corners, which is pretty good, but over time, you shoot 100,000 parts or 1 million parts, and there's some wear that happens, some degradation on those corners, and they would become more rounded over time.
Alright. Anything else about this part that's important to know?
Nope. We're good. So let's move on to the next one. Okay, the next one is this banana. I guess this is what, like a holder for utensils or something, for silverware.
So the banana doesn't become smashed in your backpack.
Ah, got it. That's great. Okay, so this is a classic injection molded part where, again, you have a constant wall thickness all the way around. Let's see. You have some holes in here that's, I guess, to keep the banana fresh or something. But
before you tell us, how do we even find the parting line? Because if you look closer, if you can show the camera, if you hold it,
yeah,
try to find the parting line here, but don't give them the answer.
Okay, so let's see if you can figure out where the parting line is. I'll just rotate it around slowly.
I struggled finding it, and he had to tell me where it is. I think I'm going to tell him.
Okay. So the parting line on these parts, and by the way, these two parts were made separately. It was not made like this. Let's see if we can take it apart. There we go.
And how do you know they're made separately?
Well, there's no way that you could make a hinge together like that in injection molding. You actually can do it kind of in 3D printing, but in injection molding, if you just think about how the steel condition required to produce a hinge that was already assembled, and then think about how would that steel be able to be removed or pull out of the hinge. There's just geometrically it's not possible.
Okay, I have a question. So to clarify, these were two different parts made different tools.
That's right.
So that means that somebody had to assemble them, put them together, right?
That's right.
Okay. So that adds to the labor cost of making the part.
It does.
So we're going to talk about that little hole in there. Was that made from a side action? There's a little hole in there. Yeah.
See if I can zoom in. Yeah, so there's a hole there, and there's a hole there, and these two pins engage with those holes, and that's what your hinge is.
Right.
And you're exactly right. These were made using a side action. So there was a little protrusion of steel that pulled out like this before the part was ejected.
Okay, perfect. So let's go back to the parting line.
Okay, parting line for this part was created right around the perimeter, all the way around here like that, except for the areas where material protrudes beyond that plane. So like right here, you can see that this material protrudes beyond, the plane of the perimeter. Same thing over here and down over here on the hinges. And so if you look really closely at those areas, ta-da, you can see a parting line there.
So the two molds that made this part, it almost looked like this from the way you're explaining it. So it looked like mold on the bottom and then mold at the top. The top part of the tool was like this, and the other one was almost flat.
That's right.
Except for these three things sticking out, basically.
That's exactly right. Yep, except for these three areas that protruded beyond that plane. Yeah, but the bottom half of the tool, or the core, so this paper would represent more or less the core, that was mostly a flat tool around the perimeter. Of course, there was, a mountain inside that created this this cored out geometry.
For this part right here, wouldn't that be, what's that term called to create that? Because that looks like a hook.
This does look like a hook, yeah. This feature right there. And this was probably also made with a side action. Yeah, if this had been made with a shutoff, and you could, I think you could make that with a shutoff. But if you had a shutoff here, the telltale sign would be that there would be a hole right there. There would be a hole right underneath your undercut feature, which in this case is actually a protrusion.
Why would there be a hole?
Where?
Why?
Because there would have to be steel that sits right in this area.
And it would have to come through the back?
It would, yeah. So you'd end up with a big hole right there. So functionally, you'd get what you want, but you'd have a big hole right here. And cosmetically, the manufacturer probably did not want that.
But you also have holes all throughout here, so wouldn't it have been a lot cheaper to produce the part with the shut-off instead of the side action? It
would have been, and it really comes down to preference. Functionally, this would have worked just fine if you had used a shutoff, but someone's preference was to not have a shutoff there and to use a side action instead.
What about the ejector pins? Do we see any marks of that?
Let's see. There we go. So ejector pins are going to be on the core side because that's the non-cosmetic side. You can see there and there and there and there.
But usually ejector pins are not going to be as visible because they'll try to hide them. Is that right?
Yeah, a manufacturer will try to hide the ejector pins as much as possible, and a good way to do that is to put them on the core side.
Right.
So you can see that there are no ejector pin marks on the cavity side, which is the cosmetic side that the world sees for the most part.
Okay. Anything else about this part worth mentioning?
No, I think that'll do it for this part.
Okay, cool.
Next one we'll take a quick look at is this remote control here. There are several different injection molded parts. There's the casing itself. These buttons here were probably injection molded. These are more of a rubber material than a hard plastic. The battery cover right here slides off. You can see a bunch of ribs right here. Let's see if they followed good manufacturing processes for these ribs, or good design processes. So we got the ribs at about 30 thousandths of an inch, which is kind of on the bottom end of what you want to make a wall thickness in an injection molded part. Typical wall thicknesses for an injection molded part are somewhere between maybe 50 thousandths of an inch to 90 thousandths of an inch, something like that. Certainly you can go thicker and you can go a little thinner as well, but 30 thousandths of an inch is probably about the lowest you want to go in general. There are some special cases where you could go lower. Okay, so we've got 70 right there, 70 there, and 30 there. So this is actually more like, what is that? The ribs are more like 40% the wall thickness of the nominal wall thickness. And you can see if we zoom in, there are definitely not any sink marks.
Where's the parting line on this?
The parting line on this, it looks like right around the top is where the parting line is.
Okay.
Yeah, it's kind of hard to see on the video, but that parting line follows the perimeter around. Okay.
Any item that has a weld line here? I don't think so.
I don't see any here. Yeah. So here's another common item that is injection molded, a computer mouse. The entire casing, the enclosure is injection molded parts. You can of course do different colors and different textures and different finishes when you're injection molding. For example, this surface right here is very smooth, whereas this surface right here is more textured, and that's just a finishing process done to the surfaces of the mold.
So after the part has come off the tool, then they do something to it?
Actually, before. Yeah, before the parts are injection molded, they will perform some kind of finishing process on the molding surfaces of that tool to create these textures.
So where would they make that? Would they make modifications to the part or to the tool?
Not to the part, it would definitely be to the tool. So if we take this part off, so like this surface here and here and here and here, all of those, well, I mean, this is the core side, and usually you don't texture the core side because it's not cosmetic. People don't see it, and it does add some cost to texture the mold. So you probably would not texture the core side. But if we looked at the cavity side, so this surface, and that surface, and then down at the bottom, all of those surfaces certainly could be textured if you wanted to produce a texture on this part. And another interesting thing to mention about texturing is that if you do texture a part, typically you'll want your draft to be a little bit greater than 1 degree, maybe 2 degrees or something like that, because the texturing can actually create very tiny, not quite microscopic, but very tiny undercuts that could be difficult to release if you don't have a little bit more draft on the part.
So when you say you're texturing, does that mean that the actual tool, this steel tool, will have like little holes in there almost?
That's exactly right. Yeah,
Okay.
I wouldn't call them holes, but I think, yeah, you get the picture. They're very, very subtle. I mean, it looks just like the texture on anything else. Let's see, we have another part that's textured. Yeah, here's a good example. So this texturing right here, if you were to cut this in half and put it under a microscope and look at, the peak and the valley between this textures, it would be, I don't know, it maybe a couple 10,000ths of an inch, hardly anything. And that's what the texture would look like on the steel as well.
So why would manufacturers want to add texture?
Texture does a few things. One of them is cosmetic. For this part here, you can see a very clear difference between the non-textured surface and the textured surface. And sometimes the texture just looks nice. It's purely cosmetic, and people like the way it looks. It also adds an element of grippiness to the part. So if there are features where the manufacturer wants to indicate to the user that you should grip here or pull here, that's a good application to use a texture. Another use of textures is that it can hide sink. In fact, it's a common method of, to some extent, hiding sink, because you can see this glossy area here. You can see all of the imperfections very easily. If there's a little scratch, or if there were a little bit of sink, it would be easy to see that because of the glossy nature of that surface. Whereas a textured surface really hides, again, to a certain extent, hides some of those cosmetic imperfections, including sink, that might occur in a part.
Anything interesting about this part you may want to highlight?
Yeah, let's take a look at this part here. So this is a Canon lens cap, and I've taken out half of it, so really it kind of looks like that. And I'll show you. So this side here, there's a spring action on it, and that comes from this little spring right here. A really interesting way that the Canon designers have designed this, and this is a great example of design for assemblability, is, let me zoom in a little bit, there are these little hooks right here. You can see them here on this side too. In fact, it's probably more illustrative to look at the side from which I've removed this tab, or whatever we want to call it. And these pins are a little bit flexible. It's maybe hard to see it, but I'm flexing them in and out right now. And that is done intentionally so that, let's see if I can get this spring back in so we can assemble it whole. There's a nice little hole right here. Our spring goes in there. And now, when the factory worker puts this together, you'll see that look at the interaction right here between those little kind of hook features. Now it clicks in place and it's done, and you don't have to use a screw or some kind of fastener to hold it in place. This is a great example of design for easy assembling.
So why is this better than using a screw?
Well, a screw takes additional time, and it's an additional part, so there's going to be a cost associated with the screw that you just don't have with this integrated design. Okay. Here are some other great examples of coring and ribs, right? So if this part was machined, you would not have these cores here. It would just be solid material filled in everywhere. But because it's injection molded and you want to maintain a nominal wall thickness everywhere, you have hollow cavities with ribs interspersed between to provide some more structural stability, some more rigidity and strength to the part.
Okay. Anything else about this part?
Let's see. No, I think that's about it for this part.
Let's take a break right here before we dive into the next.
If you found this content helpful, consider enrolling in our signature program at mypipelineacademy.com. Whether you're an individual interested in beginning a new career as a mechanical designer or a company interested in training your new engineering hires, our signature program helps students develop the practical skills they need to be productive mechanical design engineers. Seating is limited. We hope to see you there soon.